Okay, this video is worked answers to a Kahoot quiz on haloalkanes and particularly nucleophilic substitution reactions and elimination reactions of these molecules. If you haven't had a go at the Kahoot and you're a student, then go below this video and click on the link and you can have a go at the Kahoot quiz. Or if you're an instructor who would like to use this quiz in your own work, then you can click on that link and use it in your own class. Okay, so the first question out of this Kahoot quiz is actually about making the haloalkanes. So a very common way to make haloalkanes, particularly the chlorides and the bromides, the chloroalkanes and bromoalkanes, is through radical halogenation. So in one of these reactions, you have three different types of steps. There's initiation steps, there's propagation steps, and then there's termination steps. So we can immediately rule out this fourth one here. So in the radical chain chlorination of methane, what type of step is the following? So we've got a molecule here of methane and it's reacting with a chlorine radical. And you can tell it's a radical because of this dot here that stands for an unpaired electron. And on the right hand side of this reaction arrow, there is a methyl radical, CH3 dot, and HCl. Okay, so there's a radical on the starting material side on the left, and there's a radical on the product side on the right. And any step in a radical chain mechanism where we have radicals as starting materials and radicals as products is a propagation event. So we're not generating new radicals, but we're not destroying old radicals either. So it's propagating the radical chain. So the correct answer to this is the blue diamond, propagation. Question 2, which of the following of these molecules is going to be the most reactive nucleophile? So remember, the definition of a nucleophile is a molecule that has an excess of electrons and it's seeking out something with a positive charge or a partial positive charge. The nucleus has a positive charge, and that's where the nucleo part of this comes from. So nucleo is from the nucleus, which has a positive charge. So a nucleophile is seeking out a nucleus, and therefore it's something with an excess of electrons. So overall, we can rule out B, we can rule out C, because each of these molecules are electrophiles. We have a delta positive or partial positive charge on the carbon, and we have a good leaving group in the form of the alkyl halide, in the form of the halogen, which can leave with a negative charge that's very stabilized. So we know that halides are very stable anions. So now the choice is between A and D. So which one of these is going to be the more reactive nucleophile? They're very similar in structure, but A has this negative charge, whereas D doesn't. And overall, nucleophiles with negative charges are more reactive than nucleophiles without a negative charge. So A is going to be the correct answer to this, the most reactive nucleophile. Okay, question 3, which of the following is the most reactive electrophile? So the definition of electrophile is a compound or molecule that is seeking out excess electron density. It's electron loving, and electrons have a negative charge. And so therefore we can immediately rule out A. It has an excess of electrons already. It's wanting to act as a nucleophile and give away some of its excess electron density. Similarly, D is a nucleophile because it has an oxygen with lone pairs of electrons. It wants to seek out something to donate that electron density to. So it's between B and C. Now it may be tempting to say that the chloride is the more reactive because chlorine is more electron withdrawing, but really we want to look at what is the best leaving group, iodide versus chloride. So iodide is a lower row halogen, or halide in this case. Chloride is a higher row one, and as we go down the rows of the periodic table, the ability to stabilize the negative charge increases, and so iodide is a more stable leaving group than chloride. We can also talk about the polarizability of the carbon-halogen bond. So the lower row elements are more polarizable, and so in many reactions with nucleophiles, the more polarizable carbon-halogen bond will be the more reactive one. But anyway, in any case, iodide is a better leaving group than chloride, and so overall alkyl iodides are more reactive electrophiles than alkyl chlorides. And so the answer to this question is C, the yellow circle. Okay, question 4. Which of the following molecules is a protic solvent? So a protic solvent is where we have an XH group, and X is often equal to an oxygen, or most normally equal to an oxygen. So we're talking about alcohols, carboxylic acids, and molecules like that. So A is not a solvent, it's an anion, it's the ethoxide anion, and it's going to be a reagent, it's going to be a nucleophile in many reactions, but it's not going to be used as a solvent. B and C, neither of these molecules have a oxygen-hydrogen bond, so they're not protic, whereas D does have an OH group. So that OH group there, we're going to have this OH bond, and that's crucial to being a protic solvent. It can act as a hydrogen bond donor. So that makes it have special properties. So H bond donor. And those properties make it a better solvent for certain situations, including the SN1 and the E1 reaction, which involve a leaving group having to depart with a negative charge that can be then stabilized by the hydrogen bond donor. So the answer to this question is D, the green square. Okay, question 5. Which of the following of these molecules is a polar aprotic solvent? So they're all polar because they have bonds between atoms of different electronegativities. However, to be aprotic, we need to have no OH bonds. We could think of some examples where we have other elements attached to hydrogen. We'd call that a protic group, but really oxygen-hydrogen bonds are the ones we're most interested in terms of solvents. So let's just expand C here. Dimethyl sulfoxide, the structure is not drawn out, but it is a sulfur-oxygen bond like that, with two methyl groups on the sulfur, and we can draw it as this species with a formal positive charge on sulfur and a formal negative charge on oxygen. That's probably the best way to draw this. There's another form, a resonance structure, where we can draw a sulfur-oxygen double bond like this, and the two CH3 groups. Now that's probably not as important a resonance form because there's really no significant pi bonding between the oxygen and the sulfur in this molecule. So really we've got a very polarized sulfur-oxygen bond here. We've got in fact a full formal negative charge on oxygen and a full formal positive charge on sulfur. However, there's no OH bonds, and so this can't act as a hydrogen bond donor. And that is the definition of a protic solvent. We need to have a molecule that can act as a hydrogen bond donor. A here is formic acid, so we have this group here, and then OH, so that's formic acid. 2-propanol is just going to be 3-carbon chain with the OH group at the 2 position, and then D is already drawn out of the structural formula. So A, B, and D all have OH groups, and so they're protic solvents. They're polar, but they're also protic. Aprotic means without an OH group, and so that's C. So the correct answer is yellow circle C. Question 6. Which of these molecules will be the major organic compound from this reaction? So overall, we've got a carbon atom here with 3 carbon groups attached, no hydrogens, and so that's a tertiary alkyl halide or tertiary haloalkane. Tertiary alkyl halides tend to favor the mechanisms that generate a carbocation. Well, they can. Certainly in substitution reactions, they favor the SN1 mechanism. And if we go via an SN1 mechanism, we're going to generate the tertiary carbocation like this, and that's going to be attacked by the nucleophile with its lone pair of electrons. So that's going to attack, I've drawn it to show it looks like it's attacking the positive charge. I might just redraw that. We're attacking the carbon that bears that positive charge. And so when that happens, we're going to get an intermediate first, where that group is now attached to the oxygen of methanol. The oxygen of methanol still has the methyl group attached, and it still has the hydrogen, and so overall has a positive charge. But it's not going to stay like that. It's going to then lose a proton, and it's going to lose a proton probably just to the bromide that departed in this first step. So we're losing bromide in that first step, and that bromide anion can come back in, even though it's a weak base, it can come back in and pull off that proton. Electrons go onto that oxygen and we form the product, which is B. Now, A could be a possible product if we were doing this with water. That's how we would get an OH group. We would get exactly the same sort of mechanism. Water would attack and then lose a proton, and we'd end up with A, which is an alcohol. C and D really don't make any sense whatsoever. So if we look at this, if we want to expand C, we have a bond to a carbon atom, which then has 3 hydrogens attached. And then there's an OH that needs to go somewhere too. So that is an OH. And so that carbon has, in this molecule here, it has 5 bonds. Okay, and that's horrible. We never like to see 5 bonds to a carbon atom. And so that is not only not the product of this reaction, it's not a legitimate organic molecule that can exist. Similarly, D is not a very nice looking molecule. We've got it drawn so it looks like there's a hydrogen bound to that position, and then there's an OCH3. So that implies that we would have this, we would have an O methyl group, and now we've got a hydrogen with 2 bonds. And that doesn't make any sense either, that we really don't have that situation in organic molecules, and so that's not a nice looking molecule either. So the answer to this question is B, the blue diamond. Question 7, by what mechanism would compound B be formed? So this is the one we were just talking about. We said that we formed a carbocation first, in the first step, and then that carbocation was attacked by a nucleophile. So it can't be an elimination reaction, it's a nucleophilic substitution, and SN1 is the mechanism by which we have generation of a carbocation. So it's a unimolecular in the rate determining step, which is loss of the leaving group from the starting material, so the concentration in the nucleophile has no effect on the rate of the reaction. Question 8, what will be the major product of this reaction? Once again, it is a reaction of a haloalkane, but now all of the drawn possible products are alkenes. So this must be an elimination reaction. Okay, now for an elimination to occur, we must either go via E1 or E2, and in either case we must be forming the double bond between the carbon atom that has the halogen attached, and I'll just put a number next to these positions here, and I'll put 2 on each of them. So we must be losing a proton off one of those positions, either here, here, or here. And I'm just going to draw one of those protons. I'm not filling out all of the implicit hydrogens on each of those positions. So that means the double bond really has to be either across here or across here. And it could be to this other one here, but that would generate the same molecule as if it went to this one over here because of the symmetry of the molecule. So when we do that, if we lose it between these 2 positions here, if we lose the hydrogen and the bromine there, we'll end up with compound A, this one here. If we lose it, let's do this in green now. If we lose this hydrogen and the bromine, we're going to get the double bond formed across here, and that's going to be compound D here. And so each one of these are possible molecules that can form from this reaction, and they're probably both formed during this reaction. But one of them is the major product, and we can predict which one is going to be the major product from Zaitsev's rule. So Zaitsev's rule states that the alkene, the major alkene, will be the one that has the higher substitution. Okay, so what do we mean by the higher substitution? Okay, what we mean is that when we look at an alkene, we can look at the substituents on each of the carbons that form the double bond, and it's, for reasons I won't go into in this video, it's more stable to have an alkene carbon with carbon-based substituents rather than hydrogen. And so we get a slight increase in stability as we go from unsubstituted to mono to di to tri to tetra. So this molecule here, D, has 1 hydrogen and 3 carbon-based substituents. They all happen to be methyls, and so we would call this tri-substituted. A over here has 2 hydrogens and 2 carbon-based substituents, and so we would call that di-substituted. So this one, D, is the more stable of these 2 possibilities, and Seitzeff's rule would predict that is the major product from this elimination. So the answer to this question is D, the green square. Question 9. By what mechanism does the following substitution reaction occur? So we can rule out the elimination mechanisms. We're substituting a bromide here for the cyano group, CN group. And one thing to notice is that we've got the up stereochemistry here. We've got up absolute configuration, and here we've got the down absolute configuration. So this inversion of configuration is really only can happen when we have the SN2 mechanism. In the SN2, we're going to have the nucleophile. If I draw in the pair of electrons there, it's going to attack at the same time as that bromide leaves, and the transition state is going to look like a central carbon atom. And I don't know whether I've drawn the same stereochemistry there, but the overall look of this will be the same, with the leaving group departing like this, while the cyano group comes in like this. Okay, and as the cyano group comes in, the whole tetrahedral configuration of that carbon atom flips over, so it's like an umbrella inverting. And so the SN2 mechanism is where we see that inversion of absolute configuration. Now the final question, question 10, is a little bit trickier. We're asked which of the following conditions would likely lead to an undesirable result. So it's a little bit of a vague question in some ways, but let's go through each of the answers in turn. So if we increase the concentration of sodium cyanide, that will increase the reaction rate. Because the rate of an SN2 reaction is proportional to, or it's equal to, a constant K times the concentration of the nucleophile times the concentration of the haloalkane. Okay, so if we increase the amount of sodium cyanide or increase the concentration of sodium cyanide, then the reaction rate will increase. I don't think many chemists would think it's a bad thing if a reaction rate increased, normally. Similarly, if we increase the concentration of the haloalkane, we're going to get an increase in reaction rate, and ordinarily we would think that that would be a good thing as well, or at least not a bad thing. Let's skip over the yellow circle for a moment and look at using dimethyl sulfoxide as the solvent. So we said that it is a polar aprotic solvent, like this, and as a polar aprotic solvent, it is good for SN2 reactions. So in polar aprotic solvents, we can stabilize the partial charges that are being formed on the transition state, but we don't have hydrogen bond donors to stabilize the leaving group as it departs. So we don't favor the SN1, because to favor the SN1, we really want to get that leaving group to go before anything else happens. And we also, if we had a protic solvent, so if we had OH groups like this, then we can get interactions between those hydrogen bond donors and the nucleophile, and that can make the nucleophile less reactive. So overall, polar aprotic solvents are good for SN2 reactions. So finally, adding sodium iodide as a catalyst. So what would happen here is if we add sodium iodide, we have sodium and iodide ions, and the iodide ions are actually good nucleophiles. So as we go down the periodic table from chlorine to bromine to iodine, we get not only better leaving groups, but also better nucleophiles. And that's the polarizability of the iodide versus bromide and chloride. So iodide is a very good nucleophile, and it can come in, and excuse the crowding there, but it can come in and attack the alcohol bromide. and we get displacement. And if that happens, I'll just draw it down over here, we're going to get inversion of stereochemistry, if it's SN2, to give us the down alkyl iodide. And then if that compound reacts with the sodium cyanide, so I'll just draw the cyanide anion, if it reacts with sodium cyanide, it's going to go to give us some of the up cyano compound. So we're getting a bit crowded there, but we're going to get the opposite absolute configuration if we go through an inversion to the iodide and then another inversion via the second SN2. And so if we put in sodium iodide as a catalyst, we might actually get a faster rate of reaction because iodide is a good nucleophile, but then we create the alkyl iodide, this one here, it may react fast, but it is going to do another inversion and give us the up cyano group. And presumably we were doing this reaction to get one absolute configuration in the product. And we could likely get a mixture, or we could get the retentioner configuration, which we may not want. So overall, I think this is the best answer to question 10. Okay, so hopefully you found that useful, exploring some of the concepts around haloalkanes, nucleophilic substitution, and elimination reactions. Remember those key points around E1 versus E2 and SN1 versus SN2, and good luck with the rest of your studies.